If you've taken some calculus, you may have seen problems where you might want to compute areas and volumes. These may be easy to calculate for simple objects, but what about more complicated objects, like the area of some region in the plane, the surface of an airplane wing, or the volume of a region of space? One of the big themes of calculus is to solve a complicated problem, break it up into small, simple pieces, and then sum the answers. For instance, to compute the area of this, we break it up into lots of little rectangles like this, and use an integral to sum the areas. To find the surface area of this airplane wing, it's convenient to use the coordinate system to cut up the surface. But the objects we get aren't rectangles. They are approximately parallelograms. But how do you find the area of an arbitrary parallelogram? There's the base times altitude formula from geometry, but it's not clear when the parallelogram sits in R3 how you would find the area. We'll see how determinants can help us. Last time we saw the importance of invertibility and at least a dozen different criteria that help us determine if a matrix is invertible. Many of them were conceptual criteria, like the rows are linearly independent, in which, in practice, are not obvious from just looking at a matrix. The idea of a determinant is to find a single number that can be computed from the entries of a matrix that will tell us if a matrix is invertible. The formulas for inverses of 1 by 1 and 2 by 2 matrices give us a clue for how to find such a criterion. For 1 by 1 matrices, there is only a single entry, call it A, and the inverse is just the reciprocal, 1 over A. So, the matrix has an inverse if and only if the number A is not 0. So let's define the determinant of the matrix A to be A. Now for 2 by 2 matrices, recall that the inverse of the matrix A, B, C, D is the matrix D minus B minus C, A times a fraction 1 over the quantity AD minus BC. The only instance where this formula fails to make sense is when AD minus BC equals 0. And when that happens, we see that C over A equals D over B, which means that the ratio of C to A equals the ratio of D to B. In that case, the second row will be a multiple of the first row. So the rows in the matrix are not linearly independent. And by the invertible matrix theorem, this means the matrix cannot be invertible. So we see this. The number AD minus BC is non-zero if and only if the 2 by 2 matrix is invertible. So let's define the determinant of the 2 by 2 matrix A, B, C, D to be the quantity AD minus BC. Now we usually write det A for the determinant of the matrix A, but sometimes you'll also see the determinant notated by writing the matrix entries with brackets replaced by absolute value signs. But don't let the absolute value notation fool you. The determinant of a matrix can be a negative number. Let's look at an example. Compute the determinant of the matrix 1 minus 2 minus 3, 4, which is 1 times 4 minus negative 2 times negative 3. This is just minus 2. Since this number is not 0, the matrix is invertible. How about a determinant formula for 3 by 3 matrices? Recall that what we want is a matrix A to be invertible if and only if its determinant is not 0. To find such a number, recall that if a matrix is invertible, it will row reduce to the identity. So if it's not invertible, we should run into problems. Now suppose I have a matrix with entries A, B, C, D, E, F, G, H, I, and we try to row reduce it. We won't deal with all the cases, but we'll see what happens in a particular case. If we make a few assumptions that A isn't 0 and that AE minus DB is also not 0, then the row reduction looks something like this. This means that if the number delta in the bottom right corner is 0, then we will have a row of zeros and the matrix will not row reduce to the identity. So the matrix is not invertible. And if delta is non-zero, then it will row reduce to the identity. So let delta be the quantity we call the determinant of a 3 by 3 matrix. Taking a look at delta, you'll find delta equals this complicated expression. This may be a crazy formula, and I actually discourage you from memorizing it. Instead, you might consider a device for remembering it. One way to remember this formula is to write the columns of the matrix like this, then repeat the first two columns. Draw the three diagonals that go down and to the right, and the three diagonals that go up and to the right. If you multiply the entries along the diagonals and put a plus sign if it goes down to the right and a minus sign if it goes up and to the right, you'll get this formula. For instance, if you look at the first diagonal down and to the right, you see A, E, and I. And these correspond to the AEI term in the formula for the determinant. Let's do an example. Suppose we want this determinant. Then we'll form this diagram, compute the products along the diagonals as shown, and then add the diagonal products down and to the right, and subtract the diagonal products up and to the right. You will get 45 plus 0 plus 0, minus 0 minus 48 minus 0, and that equals -3. Notice that there were lots of zeros because there were lots of zeros in the first row. So sometimes computing the determinant can be really easy, especially when there are zeros. Now, I've just shown you one way to remember how to find a 3 by 3 determinant. It's cute, but I want to warn you, this idea of crisscrossing diagonals does not generalize to computing determinants of larger matrices. So I'll give you another way to remember the 3 by 3 formula that does generalize. Look at the last computation. There were lots of zeros, and the only terms that remained were associated to the single one in the first row, and they reduced to 5 times 9 minus 8 times 6. This looks just like a 2 by 2 determinant, the one you get when you ignore the first row and first column. The formula for a 3 by 3 determinant builds on this idea. The crazy expression for delta can actually be rewritten like this. What do you notice about this formula? See if you can spot any patterns. The first is that the 3 by 3 determinant depends on computing 2 by 2 determinants. In that sense, this definition is a recursive definition. And the 2 by 2 determinants have coefficients that come from the first row. The terms are alternating in sign, starting with a plus. And the 2 by 2 matrices come from taking the coefficient, looking at its position in the 3 by 3 matrix, then crossing out the row and column that it is in. If you try this with our earlier example, you'll get this computation. Note the terms alternate in sign. The coefficients 1, 0, 0 come from the first row of the matrix. And if you want the submatrix associated with the second term, you cross out the first row and the second column of the matrix. This leaves the 2 by 2 matrix 4, 6, 7, 9. So when you do this computation for the determinant, you get -3, as we expected. You'll note that the formula expands around terms in the first row, and you might be thinking the determinant seems to privilege the first row. as if the first row were somehow special. What's kind of amazing is that the determinant does not privilege the first row. You can actually compute the determinant by expanding around any row. You just have to take care to ensure that you have the correct signs on the terms. For instance, if you want to compute the 3 by 3 determinant by expanding around the second row, the signs still alternate, but you now start with a minus sign on the first term. So with our earlier example, if we chose the second row, 4, 5, 6, then we could expand like this. The 4, 5, 6 form the coefficients, but now there is a minus sign on the 4, a plus sign on the 5, and a minus sign on the 6. The submatrices are derived the same way as before by deleting the corresponding row and column of the row entries. So for instance, the submatrix associated with 5 is what you get by deleting row 2 and column 2 from the matrix, because that's where the 5 entry is, in the second row and second column. So you get the submatrix 1, 0, 7, 9. And the computation, perhaps surprisingly, turns out the same. You get -3. If we want to expand around the third row, the alternating signs would start with a plus. And there's an alternating chessboard pattern that may help you remember which signs go where. The pattern starts with a plus in the upper left corner. If the coefficient comes from row I, column j, the term should have sign -1 to the I plus jth power. You can see from this figure that the second row starts with a minus and the third row starts with a plus. So I've just told you that this number, the determinant, can be obtained in a recursively defined fashion by expanding around any row. Now here's something even more amazing. You can get the determinant by doing a similar computation, but expanding around any column as well. For example, if I look at our example and choose the third column, 0, 6, 9, then I get 3 terms here. The alternating pattern starts with a plus because it starts in row 1, column 3. The sign there is -1 to the 1 plus 3, which is 1. And the submatrices are found, as before, by crossing out rows and columns of the corresponding entries. And again, we get -3. Let's try to write down a general formula for the determinant of an n by n matrix. If we want to expand around row I, then we are looking at the entries little a sub I1 through little a sub In. Those are the entries of row I. For each of these entries, a sub ij, there is a term in the sum that looks like this, where the capital C sub ij is called the ijth cofactor. And the ijth cofactor contains a chessboard sign pattern we saw earlier, so that the term with coefficient a sub ij has sign -1 to the I plus jth power. Notice for a 4 by 4 matrix, the first row would end with a minus and the second row would also begin with a minus. That's not a problem. The key thing is that vertically or horizontally neighboring entries differ by a sign. That's why you have the chessboard sign pattern. The determinant formula contains the determinant of this submatrix, the one you get by crossing out row I and column j. The determinant of the formula that expands around columns is similar and looks like this. For each column, you have a different way to compute the determinant. This definition of the determinant, where you pick a row or column to expand around, is called expansion by cofactors. It should surprise you that you get the same answer no matter which row or column you use. The reason is too complicated to go into here, but suffice it to say that you can show that when you expand out all the submatrix determinants, you'll get a sum of products with signs that will be the same no matter which row or column you expand around. And you can learn more about this in an advanced linear algebra class. Now in mathematics, whenever you have multiple ways of getting the same answer, that's powerful, because it means you can choose which way you want to do a computation. For instance, I can see some interesting properties like the determinant of A transpose is the same as the determinant of A. That's because the rows of A are the columns of A transpose. So expanding on row 1 of A gives the same calculation as expanding around column 1 of A transpose. Another example of choosing which way I want to do a computation. If I want this determinant, can you see which row or column might be easiest to expand around? Yes, there are lots of zeros here, which is helpful. Most likely you want to expand around row 2 or column 1. Column 1 might be better because the coefficient is 1. You can now almost do this in your head, since if you expand around column 1, 2 of the terms will vanish. The official computation looks like this. And you see you get minus 24. Now we've defined the general determinant in a kind of complicated recursive formula. In practice, computing a determinant this way is rather slow because of the recursion. Mathematicians like to measure the speed of an algorithm as a function of the size of the input. So in this case, we like to say this algorithm takes order n factorial steps to compute the determinant. This means the number of steps is bounded by a constant times n factorial. So if you change the matrix size, the number of steps grows like n factorial, which is really fast. And it turns out that for a 50 by 50 matrix, which is not a large matrix in many applications we care about, the algorithm would take longer than the lifetime of the universe to compute. So we need a faster way. How can we do it? Well, the key here, as with many computations we've discussed in linear algebra, is to appeal to elementary row operations. And we'll call them EROs for short. Some EROs may change the determinant, but we'll just keep track of what changes occur. If we row reduce our matrix, which is square, to the row echelon form, then we will be able to easily compute the determinant because it will be the product of the diagonal entries. Let's see why in this example. A square matrix in row echelon form will have zeros below the main diagonal. Such a matrix is called upper triangular. If we recursively expand around the first column with entries 1, 0, 0, 0, then because of the 3 0 entries, we will have 3 0 terms. Only the first term is 1 times a 3 by 3 determinant. But that 3 by 3 determinant will also have zeros below the main diagonal. Again, expand around the first column. The only term that contributes anything is the 5 times a 2 by 2 determinant. You can see from the recursion that at every successive stage we are just picking off the diagonal terms and multiplying them together. We've just shown a cool fact that the determinant of an upper triangular matrix is just the product of the main diagonal elements. So based on this observation, what is the determinant of the identity matrix? That's right, it's just the product of 1's, which is 1. Now let's see how doing row operations may change the determinant. If you swap 2 rows of a matrix, all that happens is the determinant changes sign. You can see this most easily in the case when you swap 2 adjacent rows and then compute the determinant in 2 ways. First by expanding around row I before the swap, and comparing that with what you get by expanding around row I plus 1 after the swap. The terms will be the same except for a sign change in each one. I'll leave you to think about what happens when you swap non-adjacent rows to try to explain why the determinant flips sign in that case as well. The second row operation is multiplying a single row by a factor k. If you compute the determinant by expanding around that row, you see that multiplication by k just multiplies each term by k. So the determinant changes by the factor k as well. The third row operation is adding a multiple of one row to another. I claim that this actually does not change the determinant at all. This fact is not so easy to see, so I won't prove it for you here, but in the guidebook for this lecture, I'll provide questions to ponder that may help provide hints. So we know exactly how row operations change the determinant. In fact, to get to row echelon form, you only ever need operations 1 and 3, which in most flips the sign. Row operations to row echelon form takes order n cubed steps at most. So it's much, much faster than computing the determinant using the recursion formula. And for a 50 by 50 matrix, it won't take that much time at all on a computer. I want you to notice something. If the determinant of a matrix is non-zero, row operations will not make it zero. And if the determinant is zero, row operations won't make it non-zero. This is a key to understanding why a matrix A is invertible if and only if the determinant of A is non-zero. Why? Well, the invertible matrix theorem says a matrix is invertible if and only if it can be row reduced to the identity matrix. But because the identity matrix has determinant 1, row reducibility to the identity means that the original matrix must have had non-zero determinant. Thus, we've shown the following. Here's a theorem. A matrix is invertible if and only if its determinant is non-zero. All right, we've defined the determinant, and we know that it's 0 if and only if the matrix is not invertible. But if we get a non-zero number, does that have any meaning? Indeed, it does. If you have n vectors in Rn, those vectors span something called a parallelepiped in a natural way. Just form all the possible sums of those vectors, including the zero vector, and you will have the corners of a parallelepiped, an object formed by pairs of parallel sides. So a two-dimensional parallelepiped is a parallelogram. And this is what a three-dimensional parallelepiped looks like. If you have a square matrix with columns v1, v2, v3, then the determinant actually tells you the signed volume of a parallelepiped spanned by those three vectors. That means the number you get is the volume of the parallelepiped, but its sign may be positive or negative. And which sign it is depends on the order of the vectors. For instance, for a parallelogram, if v2 is counterclockwise from v1, the sign of the volume is positive. Otherwise, it's negative. In 3 dimensions, you use the right-hand rule on v1 and v2 and compare that to the direction of v3. If they're in the same general direction, positive dot product, then the sign of the volume is positive, else it's negative. In higher dimensions, the sign will be positive if the vectors v1 through vn are oriented in the same way as the standard basis vectors, and negative if the orientation is mirror reversed. It's worth pointing out here, since the determinant of A transpose is the same as the determinant of A, the determinant is also the signed volume of the parallelepiped formed by the rows of A as well. In the simplest example, let's look at a rectangular box with side lengths A, B, and C. The vectors that form the sides from the origin are A00, 0B0, and 00C. For fun, let's put them in the rows of a matrix A. This is a diagonal matrix, and the signed volume is the determinant of this matrix. And what is that? Well, it's just the product, little a times b times c. So we see that the determinant indeed gives the volume of the rectangular box. And if c were 0, the volume of the box would be 0 since it has no height. But the determinant will also be a times b times 0, which is 0. And if the matrix were the identity matrix, then the box would be a unit cube with volume 1, which jibes with the identity matrix having determinant 1. It may be helpful to think about another interpretation of the determinant. Look at the linear transformation that takes the standard basis vectors e1 through en to the column vectors v1 through vn in the order given. This is just the transformation t of x equals a times x, where a has columns v1 through vn. Then if you take a blob like a smiley face and watch where it goes under the transformation, it may get deformed and stretched, and it may get mirror reversed. The determinant tells you the factor by which the volume of that smiley face gets stretched. And the sign tells you whether the smiley face got mirror reversed. If so, the sign is negative. These geometric interpretations of the determinant are useful. For instance, if you think back to the problem of finding the surface area of a strange shape like an airplane wing, where we cut up the wing by coordinates and got little parallelograms, you can use the determinant to help compute those areas. Any formulas you may have learned from calculus to find surface areas use some version of this idea. Another property of determinants is that they behave well under multiplication. It may be a surprise to you that the determinant of a product is the product of the determinants. Let's look at this example. We have two matrices, A and B, and their product, AB. When you compute their determinants, you get 3 and minus 2, and their product has determinant minus 6. It's rather surprising that these things should be related at all. You could try to prove this using the cofactor definition of the determinant, but it's a tedious verification and it's not that enlightening. On the other hand, if you think of determinants as scaling factors, this property becomes obvious because the product AB corresponds to the linear transformation T of x equals A times B times x. And that first performs B, scaling the face by a factor of minus 2, and then performs A, which scales the face by a factor of 2. So the total factor in scaling is clearly 3 times minus 2, which is minus 6. Just a warning now, since you may be wondering about addition. Do determinants behave additively? It is definitely not the case that the determinant of a sum is the sum of the determinants. You might pause and try some very simple examples to convince yourself of this fact. Another thing you might be able to see from the geometric interpretation is that a matrix A is invertible if and only if its scaling factor is non-zero. If it is 0, then linear transformation is basically collapsing a region with non-zero volume to 0 volume. And as such, there will be points that get mapped to the same point, so it's not possible to find an inverse transformation. Moreover, you can see some of the equivalences in the invertible matrix theorem. For instance, if the columns of a matrix are not linearly independent, then one vector is a linear combination of the others, so the corresponding parallelepiped will be a flat parallelepiped and have 0 volume. So it is clear that the determinant is 0. Let's conclude our lecture by giving intuition for why the determinant measures the volume of a parallelepiped. The basic reason is that the determinant formula gives the right answer for a rectangular 1 by 1 by 1 box, which corresponds to the identity matrix, and that elementary row operations change determinants in exactly the same way as they change the signed volume function. So if I can take any invertible matrix to the identity matrix with row operations, then the determinant and signed volume function must be the same. First, if you swap two rows of a matrix A, the object has now been mirror reversed, so the signed volume flips sign. Second, if you multiply a row by a constant k, then you've just changed one dimension by a factor k. So the signed volume gets multiplied by k. Third, if you add a multiple of one row to another row, then the associated parallelepiped changes by a shear motion. But you may remember from geometry that if you take a parallelogram, a parallelepiped, and apply a shear motion, the shear does not change the volume nor the orientation, so the signed volume stays the same. If you recall, we noticed the same changes were true of the determinant when we did the row operations, so the determinant is the same as the signed volume function. In this lecture, we've seen that the determinant of a matrix A is really an important number that can tell us when a matrix is invertible and what the scaling factor is for the associated linear transformation. We'll use it in some important ways in the coming lectures to begin to understand one of the most important concepts in linear algebra, eigenvectors and eigenvalues.